All right, building these function problems, we have to actually build our own function. We don't get a problem. We don't have the function written into the problem like our last two examples. So here we have an island, that's this point I, is 2 miles from the nearest point P. That's a perpendicular distance. The shortest distance between a point and any object is a perpendicular distance. So that's and that is to a straight shoreline. A town is 12 miles down the shoreline from point P, so 12 miles. If a person can row a boat an average speed of 3 miles per hour and the same person can walk an average speed of 5 miles per hour, then write a model that expresses the time t that it takes to go from the island to the town as a function of the distance of x from point P to where the person landed the boat. So what it appears in this problem is that it would take too long, it would not be efficient, to row just 2 miles to this point and walk the rest. And it definitely would not be efficient to start here on your island and row to town because that's only a rate of 3 miles per hour. We want to get some walking in because we will walk faster than we row the boat. So the problem is indicating that we want to land somewhere over here. So we want to write this as a function t of x. And so t is for time. So we have to find the time we're going to row our boat, let's assume it's this dotted line here, to some point x miles away from P. And then we're going to walk from this point to town, which we're going to have to figure out this distance. And we'll find that time. So what it appears to me is that I'm talking distances, I'm talking rates, I'm talking time. I think we need the formula distance equals rate times time. And what we should do is with this formula, since we're looking for time, let's solve it for little t. So divide over the r. So time is equal to distance over the rate. And we have the rates. We have the boat rate of 3 miles per hour. We have the walking rate of 5 miles per hour. What we're going to have to do is we're going to have to find the distances. So if we do our rowing time, again, t equals d over r. We know that the rate for rowing is 3, so we'll put that in for r. The distance I need to find, again, I'm guessing it's this dotted line, which is forming a right triangle. And so I think we're going to use the Pythagorean theorem here. I'm going to let a equal 2, b is going to represent the x, and the c will be our capital D, the distance. So capital D squared is going to equal 4 plus x squared. And then to solve for capital D, I'm going to take the square root of that expression, 4 plus x squared. No plus or minuses here again because distance has to be positive. And I'm going to put that expression up here for D. And that's now my time it takes to row. Next, I'm going to look for walking time. So again, t equals d over r. Your rate is now 5 miles per hour. We have to find this distance right here. Well, what I do know is the total distance is 12, and we need to take away x miles from it to get this distance, so it'd be 12 minus x for that distance. Let's put that in for d, and that's my walking time expression. So my function is capital T of x is equal to the square root of 4 plus x squared over 3 plus 12 minus x all over 5. There's my function. Now, we may have to use that function because now we're going to be asked, what is the fastest time to go from the island to town? So if we want the fastest time, we want the least amount of time traveling. That's a minimum. So what we're going to want to do is we're going to want to graph this function in our calculator. And we'll find the relative min. All right, so let me bring my calculator over. Well, first let's see, I think we got to set up our domain. All right, your smallest possible x would be 0. Your largest possible x would be the distance down the beach to the town, that's 12. Y min and Y max, let's see, the largest possible Y value. Well, let's see, the longest distance would, or I should say the greatest amount of time would be as if we rode all the way to town. So that's x equals 12. So that turns this into a 0. So 12 squared, then take its square root, would be 12. So 12 plus a little bit more of a decimal, that's going to be approximately 4. So let's say the largest value for y will be 5. That should cover everything. All right. So change your window, and again, I'll get my calculator and we'll enter it as well, and we'll make the graph. So let me go get my calculator over here. There we go. So our function, we need a fraction, alpha y equals number 1, and that was second square root 4 plus x squared all over 3, and then we're going to add to that the fraction alpha y equals, to get our fraction command, 12 minus x on the top all over 5. Then I'm going to go to my window. There's my x min of 0, x max of 12, y min 0, y max 12. So if I graph it, there's my picture, and there's a definite relative min right here. Now, if we find, and I want to point this out and show you with this example here, that there are rounding errors that can occur, and I want to explain why it happens. So if I go to second trace, let's say we're going to find the minimum, number 3. I'm going to do this a couple times just to show you what's going on. I'm going to say that my left bound, I'm going to type it in as 0. And my right bound, oh, let's say 5. That's so somewhere in between there, and I'm just going to hit enter. 1.500000008, 2.933333333. I'm guessing this is a rounding error. So if I were to type in just 1.5, there is the same 2.9333333. Now, I'm going to do the minimum one more time just to show you that it's possible to get a different value here than that 1.500000008. So second trace, do the minimum again. This time I'm going to go from, oh, let's say 1 to, let's say, 2. Oh, a different value. Now it's an 11 there. Let's try second trace number 3. Let's go 0.5 and a 3. 1.499997. So it's a rounding error. Now what the calculator is doing, it all depends on your left bound and your right bound. And what the calculator is kind of doing is it's bouncing back and forth. It's going back and forth looking for a smaller y value, and it does this really fast. So it starts here maybe at 0.5, then it goes over to the 3, and it says, no, wait a minute, that value's bigger, let's go smaller. So it might split the difference. Okay, if it's that y coordinate's still not bigger, it splits it again. I found a smaller y, then it splits the difference over here. And it keeps doing this back and forth, back and forth, back and forth, and it goes out to 12 decimal places. And when the y has the same 12 decimal place values 3 times in a row, then whatever that third x value was, as it's bouncing back and forth here, is going to give me the answer of x. So when you see a 1 point something with a bunch of 9s, or 1 point, in this other case 5, with a bunch of zeros, it's definitely a rounding error. Type it in, round it to where it's obviously jumping out at us at 1.5. Type it in, and you get the same y value. Okay? So what this is telling us is that you need to land your boat. Oh boy, I'm probably going to get all kinds of blue stuff here. All right, you need to land your boat 1 point, yep, there's all my blue. Let me go back, there we go. You need to land your boat 1.5 miles from point P. If you do that, it will take you a total of 2.93 hours, because it's hours because our rate was in miles per hour, to get to town. All right, last example. Again, a word problem, no function given, we have to build our own. An open box with a square base is to be made from a square piece of cardboard 36 inches on each side by cutting a square. So the lighter shade of gray is going to be cut out from the corners, and then turn these sides up on the dotted lines to build a box. Find a function for the volume of the box. All right, so the volume of a box, that formula is length times width times height. So V of x, where's my length, my width, my height? I got to put all x's in those blanks. So looking at my cardboard here, I know it's 36 inches on all 4 sides. What I don't know is how big of a square piece I need to cut out. So all these light colored grays are going to be x by x squares, because I don't know that. That's my variable. Well, if you think about then folding this flap up, this x is now the height of my box. So I'm going to put an x in there. Then down here, the base of my box, where these dashed lines are, this is going to be my length and my width. So to find that length, it could be any one of these 2 adjacent sides. It's going to be 36 inches minus this distance of x minus another distance of x. So that's going to be 36 minus 2x for both the length and the width, because we have a square base. So these 2 sides are the same. So multiplying the 2 binomials together, we'll just write it as the power of 2 multiplied by x. I opted to put that in front. Again, if they ask us to actually find what x you need to cut out, what's the x by x square to maximize your volume, again, we're going to go to the calculator and graph this. All right. So my window, x min 0, nothing cut out. My x max, I can't cut out anything bigger than going halfway across, because then I would cut out all 4 squares and there'd be no base left. So half of 36 is 18. Graphing this, and I'll be honest, what I did to find my Y max is I kind of graphed it first and traced to find some numbers. So here's another case, and again, I'll bring out the calculator and show you how to do all this again. 5.9999, where again, I think it's 6, which I know it's rounded to 6, because think of this for right now. This number times this number times this number. If this was a decimal, this area would have a huge number of decimals. So this has to be a 6. And I typed in a 6 in the trace mode, and there's my same answer. So we have to cut out a 6 by 6 square, and this is going to be the maximum volume of my box. So again, let me bring my calculator over. So y equals, let's clear that out. We said x times the binomial 36 minus 2x, and we were going to square that. So this is in theory what I did. I went to window and I changed my x max from the last problem from 12 to 18, and I graphed it, and I can clearly see I am way off the screen up here. So I hit trace, and I typed, well, here's 9 at 2,916. And then I just punched in some arbitrary numbers like a 4, a 5, just to see my values. They're all really big here in the 3,000s, if you will. So I would change my window, take my Y max and maybe make it 4,000. Y scale 1,000. Graph it. I want to see the whole curve. So there's my max right there. So once you see the whole graph, you can see where your max is. We're going to go second, trace, number 4 for the maximum. Left bound, let's see, 1, 2, 3, 3 or 4. Let's try 3. That's pretty good. And then we were over there at, what, 9 when we first started. There we go. There's my relative max. Hit enter on the guess. And again, there's the 5.99999. I believe it's a 6, so you just type in a 6, and you still get the same Y value. Now, same thing holds true if you do choose different numbers and it comes up as 6.000011. And if this has no decimals to it, then we definitely know that this is an integer. All right, and there's the last of our videos.